This is the third video in the series on gravity, in which I am describing an energy shell that, at least an imaginary energy shell that surrounds the Earth and that represents the location of the Moon at all times since it left the Earth. It cannot move from the surface of the shell because its energy, its total energy, the sum of its potential and kinetic energy, remains constant. And I'm going to give you the equations today to describe how that works. First of all, let's go over a couple of equations that we're very familiar with, I'm sure. Let's get them in clear view. Everybody, I think, is familiar with the centrifugal acceleration, the force being the mass times that acceleration. In a circular orbit, or in fact in any curved path, the radius of that curved path and the velocity determines the acceleration that tries to make the body move in a straight line and leave the orbit. So v squared over r is the equation for that. Then we have Newton's equation that opposes that. And this is the gravity equation that says that the mass of the Earth, in the case of the Moon, the mass of the Earth times the universal gravity constant g, divided by the radius of the orbit of the Moon around the Earth, assuming it's circular, gives you the force of gravity, or the acceleration due to gravity, and these two are equal when the Moon is in a stable orbit. And that is the usual explanation for the Moon remaining in orbit, and involves a force of gravity. But I'm going to use energy instead of force as the reason why the Moon stays in orbit. And here we have, if the Moon left the Earth with a velocity which determines the kinetic energy of the Moon, the velocity being equal to v naught squared. That's equal to twice the mass of the Earth times the universal gravity constant, multiplied by the reciprocal of the radius of the Earth minus the reciprocal of the initial radius of the Moon. That would be the maximum radius of its initial elliptical orbit, and that determines the velocity. And this energy, which is the mass of the Moon, this is the velocity per, or energy per unit of mass of the Moon. So the mass of the Moon times this velocity squared gives you the kinetic energy of the Moon. This energy has remained constant since the Moon left the Earth, and it went to an energy shell, and this is the equation for the radius of the energy shell. The radius of the energy shell surrounding the Earth, that is now the location of the Moon on its surface. This radius, r0, is equal to the radius of the Earth divided by 1 minus the radius of the Earth times the square of the initial velocity of the Moon, that's the velocity with which it was ejected from the Earth, divided by twice the mass of the Earth times the universal gravity constant g that Newton referred to. So that gives it the energy. Now here are some relationships between the different kinetic energies involved, or squares of velocities. The escape velocity from the Earth, which is about 25,000 miles an hour squared, is equal to the ejection velocity, the initial velocity of the Moon, plus the square of its velocity in its circular orbit, which is approximately the same as what it is in now. So if you add the kinetic energies of the Moon in its circular orbit with the kinetic energy of the Moon in its initial kinetic energy, from which it was ejected from the Earth, you get the escape velocity of the Earth. And that's true of any satellite body, as we'll see later when we talk about the planets and the Sun. Now, in the equation I showed you earlier, you can substitute the escape velocity of the Earth for twice the mass of the Earth times the force of gravity, times the, gravity constant, divided by the radius of the Earth. And that's true of any body, so that's why I've just put a plain R. That's true of any escape velocity. And the circular velocity, the orbit in the the velocity in the circular orbit of the Moon is equal to the mass of the Earth times the universal gravity constant divided by the radius of the Earth. Now let's look at the next equation. And these are all the equations that I've used in discussing the force of gravity. Here we have the final circular velocity of the Earth, which it eventually will get. The initial elliptical orbit gradually changes into a circular orbit for various reasons that I'll describe perhaps at some other time. The radius of the circular orbit is half the initial height of the Moon on its first orbit, which was a very, very narrow elliptical orbit, divided by 2. That gives you the circular radius. The period, as with any period in a circular orbit, is equal to the radius of the circular orbit divided by the velocity in the circular orbit. Now this is a period which is in seconds per radian, not per cycle. If you want to use cycles, you have to multiply the r by 2 pi, but the radians are more of a natural unit of period. Frequency is the reverse of that in radians per second of the circular orbit of the Moon. Now those are the equations that I used, and for the next video I'll talk about the planets and the Sun, because we can there compare several satellite bodies and see if they all have values that are consistent with my theory. That's the end of the third video on gravity. Thank you very much for listening.